Good morning. Welcome to Friday. You've all made it this far. I'm very pleased to introduce Anton Mellit, who's going to speak to us about combinatorial expressions for the nabla operator.
Does it work? Oh, great. Thanks to the organizers for inviting me. Actually, so some anecdotes. So about, what was it, 5 years ago, Pasha Pilarski wrote to me about this conference and he asked me for a title. And it was very strange. He asked me for a title 1 year before the conference. And I replied, how do I know which problems remain open in 1 year? And, but it turns out that the title survived even until now, which kind of curious. So this is joint work with Erik Carlsson. And how do I, okay. Well, okay, I will look here. So before I start explaining, I want to explain some idea, general idea, and it's better maybe explain on this example. So we fix the skew shape. So it's skew shape, meaning you have two Young diagrams and you remove one from the other. For instance, this is a perfectly valid skew shape. And we fix content, which for us in this talk, content means a multi-set of integers. So several ones, several twos, and so on. For instance, 1, 1, 2, 2. And then we all know that it's good to count semi-standard Young tableau of shape, given shape and given content. For instance, in this case, we have exactly two tableaux. Please ask questions if it's not clear. Okay, so and then what is a clever way to sort of formulate the answer to this counting problem? Is the following. So to a shape, we associate a skew Schur function. So it's a symmetric function. It's a linear combination of ordinary Schur functions or other use your favorite basis, whatever. And to a content, we also associate a symmetric function by multiplying together the multiplicities. To each multiplicity, we take the corresponding complete homogeneous function, and then we multiply all of them together. And the answer to the counting problem is given by the scalar product of that Schur function and that homogeneous function. For example, in our running example, so it's this corresponding skew Schur function turned out to be S22 plus S31. And the homogeneous function, the product of two complete homogeneous functions, is this combination. And then you take the scalar product, means you count how many, like there is this S22 here, and then there is S22 here, and there is S31 here and 31 here. So the scalar product is 2. And that's exactly the 2 from the counting problem. Okay. So now let's just focus a little bit on this formula, this scalar product formula. On one side, this is something coming from the shape. On the other side, something coming from the content. And the point is that the dimension of the space of symmetric functions of that degree is the number of partitions. And it is smaller than both the number of possible shapes and the number of possible contents. Because in contents, you can have like 3, 1, 1, 3, for instance. They're considered different, strictly speaking. And so there must be something interesting hidden in this, just in this statement. That, if you want, like for instance, if you this statement implies, for instance, that if you change the content by permuting the integers, for instance, instead of having 3 1s and 1 2, you can have 3 2s and 1 1. The number doesn't change, which is non-trivial, just from the definition. But for the, if you now fix, maybe you fix the content, but you change the skew shapes, then it also tells you that the counting between different skew shapes must be related somehow, and that's sort of there is interesting combinatorics there. Okay, so that's one thing. And here is a sort of, so yeah, keep in mind is there are always variations of this. So here we simply fix the content and fix the shape. And we count like each. Okay, now suppose we want to count some other kinds of skew, some other kinds of semi-standard Young tableau. For instance, you fix the set of possible entries, but you don't fix the multiplicities. Okay, so say the entries are from 1 to k. Or another version of this problem. Suppose you want to count semi-standard Young tableau with entries positive, non-negative integers, but each entry is weighted by a power of q, by the corresponding power of q, right? You can formulate many interesting, maybe, I don't know, you have whatever, your favorite counting problem about tableau. And this statement will still be true that in each of these situations, there exists a symmetric function that encodes the answer. So there exists a symmetric function such that for every shape, for every skew shape, the answer is given by the scalar product of that symmetric function with the Schur function for that shape. So, okay, that just follows from this linear algebra from the previous slide. But then it's more, so how do you find this f? Well, one way to find f is fix some easy shape which you can easily handle. And a collection of shapes. And that will give you scalar products of f with some functions. And maybe you can recover f uniquely.
Good morning. I'm sorry if this.
Yeah. What's the?
All these stupid things that show up on my phone that I don't want on here.
Can you please mute yourself?
That's it. Okay. So that's our approach. We fix some easy shape. And here is how we can do it. For instance, you can consider shapes of this form where you have a bunch of vertical bars with no overlaps. Okay. Then in the first problem, when we fix the entries from 1 to k, but we don't fix the multiplicities, it's very easy to count the shapes of the standard semi-standard Young tableau of this form, because so in each column, in each bar, you have a collection of distinct entries out of those k. That's given by the binomial coefficient. And so you know that your unknown function, scalar product with, so the Schur function for this shape is just the product of the elementary symmetric functions. So you know the scalar product of f with elementary symmetric functions. It's just the product of the binomial coefficients. Oh, m is k. K is the number, the maximum possible value of entry. And so, okay, but that's uniquely recovers f. Namely, the dual basis for the elementary basis is the so-called strange symmetric functions. They are, if you take monomial symmetric functions, you apply this involution, you get those ones. So you get expansion of f in terms of those strange symmetric functions. Okay, so, and yeah, of course, you can also count for the horizontal bars, then you get expansion in terms of the monomial basis. So somehow I proved these identities for you. For instance, I proved that this is equal to this without writing down too many formulas, just by pure thought somehow. Okay. Of course, you could also compute the whole thing by hand, and that's okay. I just want to demonstrate the approach, because in the other situation, this will not be possible to compute things by hand. Okay. So this is somehow the first part. I tried to explain the approach in this classical situation of counting Young tableau. Semi-standard. Yeah. Now, there was a question. I don't know the question. What was it? Okay. Yeah, maybe I should have said that semi-standard tableau is a filling of a diagram which strictly increases along the columns and weakly increases along the rows. So now this definition is modified. So it's this, I think it's a very beautiful object, this P-tableau, which I think it deserves to be studied much more. So introduced by in the preprint of Gessel-Viennot, which is not published preprint. Actually, it's not so easy to get it. And even if you get it, it doesn't have any pictures. There are references to pictures, but no pictures. So you have to ask Christian Krattenthaler to send you another file with pictures. So yeah, but then Shareshian-Wachs have a paper where sort of they again explains everything relevant. Okay, so a unit, everything is depends. Right, in the first part we had a shape and the content. We will have to generalize. Let's generalize the content, the meaning of a content. The new thing, which we'll call instead of content, we consider a unit interval order. So what is the unit interval order? There are many definitions, but for me, so you have a linearly ordered set. So linearly ordered, you can have take bijection. You can say it's integers from 1 to n, for instance, if it's finite, you don't lose anything. And together with a second relation, and that relation is also order relation, and we call it much greater than. So we can compare numbers normally, but then you have this other thing where you say this number is much greater than another number. And that's also an order relation, but it's not linear order. Some numbers become incomparable. So the axioms for this much greater than are the following. So if some number a is much greater than b, then a must be just simply greater than b. And this thing. So if a is much greater than b and b is simply greater than c, then a must be much greater than c, or in the other way around. Right? So very clear intuitively. Equivalently, there are, you can so the dig pass Hessenberg function from Juliana's talk yesterday. It's the same thing, at least in the case when the set is finite. So let me explain here how a dig pass encodes this sort of much greater than order. So here is my dig pass of length 5, and the numbers, the n elements of my set are on the diagonal here, 1, 2, 3, 4, 5. And to each pair of numbers, I can look the corresponding. There is a corresponding box, and it can be inside, under the pass, or above the pass. So I say that number is much greater than another number if the box is outside of the pass. So here in this picture, for instance, you see that 3 and 1 are still under the pass, but 4 is already 4 and 1 is already 4 is too much. So 4 is much greater than 1 here, and 5 is much greater than 1, and there are no other much greater than statements. Okay, so it's a toy we play with. Yeah, I just wanted, so there is a slang. Whenever a is, so b is greater than a, but not much greater than a, then somehow b is too close to a, right? It's after a, but it's a bit close. So we call it we say a attacks b. So in here in the picture, 1 attacks 2 and 3, and 2 attacks 3, 4, 5, but no other. And 3 attacks 4 and 5, 4 attacks 5, and so on. Okay, so all this is very much inspired by the paper by Haglund, Heyman, and Loehr about about explicit combinatorial formulas for Macdonald polynomials. So they have all these attack things. It's just sort of axiomatization of that. Okay, now we fix this unit interval order, and we are going to consider certain fillings of a shape. So we fix a skew shape, and a P-tableaux, P stands for our unit interval order. A P-tableaux is of some shape is a filling of the shape by entries of P, such that the following things hold. So you should what is meaning of these rules? You take the usual rules for the semi-standard skew tableau, but you use this much greater than in a clever way. If a number is on top of another, in the classical situation, we would ask that A is less than B in this on the right. Now we are asking that A is much less than B. And if two numbers are in a row, then before we would say that B is greater or equal than A. But greater or equal means not less than A. And that's why we put here, so A, if A is to the left of B, then A is not much greater than B. So it's, yeah, let's see maybe. So somehow you make one direction much stronger requirement, but in another direction you have weaker requirements. In the horizontal, weaker requirements. But somehow, so there are some observations you can make that imply that your theory somehow is still a little bit similar to the usual counting of Young tableau. And here it is. So one thing you can observe is that if you can put A, so if you can put A on top of B, then you cannot put it to the right of B, and conversely. So A on top of B is allowed if and only if B to the left of A is not allowed. Or you can prove, that's a good exercise, that if in some shape A is diagonally above, to the left and above B, then A is less than B. Notice that if A is here and B is here, because if you have a skew shape, you must have something here and something here. So you need to use that to prove this. And then here is a more exercise that if you have two neighboring diagonals in the skew shape, and you know that A is in one diagonal and B is in some other diagonal, it completely determines if A is supposed to be higher than B or lower. If you played with semi-standard tableau, that this is very useful property. So yeah, any two elements in neighboring diagonals know their relative position. Okay, so just some sort of introduction of this. And so when Gessel and Viennot, they consider just vanilla with this P-tableaux, but Shareshian and Wachs, they also have a Q weight of such things. So you can simply count this tableau, that's fine. That's already interesting. There are conjectures about that coming later. And but also it's good to count them with Q weight. So the definition of the Q weight of a P-tableaux is that you consider some pairs of numbers A and B, such that A attacks B and A is to the left of B. Of course, you can replace to the left by to the right. It's you get similar equivalent count. Right. So one important remark is that if you have a column, then remember that in the column the numbers are increasing fast. So they cannot be compared. They are don't attack each other. So you never have ambiguity in this. You never have two elements which attack each other in the same column. But yes. Yeah, yeah. In a column, the question was if it's So it's in the column. To the left means in the column to the left of the column of that one. Right. And here is a theorem that generalizes the counting statement for ordinary tableau. the following. So for take a finite unit interval order or a Heisenberg function, if you like. So it's the same. So statement is that there exists a symmetric function, which we denote chi p, such that for any skew shape, the q-weighted number of p-tableaux of that shape is given by the scalar product of chi p and the corresponding Schur, skew Schur function. Okay, so this the shape doesn't, the contribution of the shape doesn't change to the statement. It's still the Schur function. The one difference is that chi p now has some q's in it, for instance, but the statement is still true. Okay. So this chi p, up to some simple, like applying some involution and symmetric functions or pletistic substitution, is basically the chromatic symmetric function. I think it's just the involution applied to the usual chromatic symmetric function to make this statement correct. Also, it's called sometimes LLT function of that unit interval order. So, okay, now I understand I needed some examples already earlier, but so here is example. One unit interval order is the unit interval order. It's the, when you say I is much greater than j, if I is greater than j plus 1. In fact, you can see that if you now allow real numbers with this condition, then you can embed any unit interval order in the unit interval order of real numbers. I think that's why it's called unit interval order. Okay, so that's already interesting. So let's see. Suppose what does it mean to have a p-tableau of shape single row? So a sequence is a p-tableau of shape n, or single row size n. If there's, I write this inequalities that must be satisfied, and then I get this. I equivalently translate them in this way. So, so if we start with an and then consider an minus 1 and so on, then you can observe that if an is 0, then the object you get, the set of sequence, is just what's called area sequence of a dict path. So what's the area sequence of a dict path? You draw a dict path like this. It's the same dict path, but it has completely different role in this discussion. It has nothing to do with the previous picture. So when you have a dict path, you can count for each vertical step, how far are you from the diagonal? So you start with 0, then you get 1, then you get 2, and it's again 2, and then it's 3. So this is the area sequence of the dict path, 0, 1, 2, 2, 3. And of course, you get a dict path if and only if the next number is at most 1 plus the previous number. And that's exactly our inequalities. So, but except that you have to put the numbers backwards. So that's why I put them here backwards. Okay, so dict paths are in bijection with p-tableau for this particular unit interval order, satisfying additional condition that the last entry must be 0. So there is another trick which you can use. Instead of putting numbers backwards, you can put them, take the negatives of the numbers. But not so important, I guess. So so this is really nice, no? It turns out you can equivalently you can sort of describe the set of all parking functions as a set of p-tableaux satisfying some conditions. So so parking function is some sort of, it's a dict path plus a labeling of the vertical steps satisfying some extra monotonistic conditions when two steps are go after one after another. But for this, maybe it's more interesting to think about the other example. Suppose, well, now we understand that fillings of a single row are dict-paths. Now, what if you have more complicated skew shape? What is it? Well, every row still has a dict-path, right? But what's the relationship between the two paths? It turns out that you get nested dict-paths. So one must be on top of another. Think about, for instance, think about this part here. This cell here corresponds to the area sequence equals, in this place equals 2. Yeah, here the side is 2. To have a nested path, you can use only this cell. You have to go like this. So the area sequence of the nested path must be at most 0. And similarly, you get these inequalities. And inequalities for a nested dict-path will be the area sequence of a bigger path minus 2. And that's precisely our the relation of our much greater than relation. Okay. So that's kind of a cool observation. So now think, we could, if we want, now we want to enumerate dict-paths in some way, we could just use this the theorem of Shareshian-Wachs, except one little thing, that we have to impose these conditions that an equals to 0. And that's not imposable in their calculus. So it's a real problem. It seems like a little thing. You don't want to consider some non-interesting sequences, but the whole counting breaks down. So it's when you put, well, yeah, if you put two bars on top of another, one on top of another. So the question is, which shapes precisely correspond to nested paths? I'm saying that if you have 2 bars, one on top of another, then the path corresponding to the one above will be nested inside the path corresponding to the one below. So for this statement, you don't even need skew shapes. It just, yeah. Any other questions for this one? Okay. And then once you start thinking about this problem, then there is this, it's very natural that somehow the point is that the skew shapes is not all possible shapes you have to consider. And here is the explanation. So what is the meaning of a skew shape, of like, what's the main property of shapes in the Young diagram calculus? If you have a skew tableau, here it is. So take Young tableau, take a set of cells containing all numbers less than k. And it's always again a skew shape. It's basically the whole point of skew shapes and the tableau and so on. Yeah. But for our definition of P-tableau, it is not so. So let's look at this particular P-tableau. So you see that, that's the first big example of a P-tableau, right? The unit interval order is the same as before. So you see that in each row, numbers can decrease, but at most by 1. And in each column, they must increase, but faster. So for instance, so one number is on top of another, it must be at least 2 plus. The difference must be at least 2. So I drew this tableau, and then I take all entries less or equal 5. And I get this picture. It's not skew shape at all, right? So let's ask what kind of properties does the new shape satisfy? So let's first think about the columns. Columns are really fast increasing numbers. So if you say less or equal, you still get some part of a column. So that's okay. Each column remains a column. But the only thing that can change is the height. So the heights of columns of an ordinary Young diagram must not increase. But here we can increase, the height can increase, but only if a column ends with the 5. Because if you have a 5, then the number to the left of it can be 6. Otherwise, it has to, if it's not 6, then it is 5, 4, 3, and so on. So that's, so let's axiomatize this. So what we will get is called generalized shape. So a generalized shape is the shape of the form. So here I use the transposition, meaning that I have several bars, but transposition means the bars are vertical. So this means I have a bar of size lambda 1, lambda 2, and so on, lambda n. Okay. So in this example, the lambdas are 1, 2, 2, 3, 2. And some cells of the shape will be marked with stars. So star is that 5 that we had. It was special. So some cells are marked with stars with following conditions. So a star can only be placed in the bottommost cell of a column. So at most 1 star in each column, and it's always in the bottom. And the second is that either your columns, the next column is shorter or equal to the previous column, like in the usual case, or there is an exception. So if the ith column has a star, then it's allowed to be longer, just one longer. Okay, so here, for example, we have these 2 stars, which allow these 2 become larger than 1. So we have exceptions to the Young diagram rule. That there are 2 exceptions, but then there is this 2 here is smaller than 3, so it's okay. Or this 2 here is equal to this 2, so that's okay. Okay, so exceptions are allowed if you have a star, and the exception is at most by 1. Don't be too greedy. Okay. So very natural definition of a new definition of a skew shape in the context of P-tableaux. Okay, so here is the sort of definition. So from now on, we will be dealing with unit interval order plus some extra data. That is in a number k, so that the k greatest elements are maximal for the. So it's sort of. Do I have? Yeah. So you have this. You choose a bunch of maximal elements, and they're supposed to be all the way to the right in your unit interval order. So this new information depends only on the number k. So, and these elements will be called special. And on the other hand, we will have shapes with k stars. And also we will fix exactly what we are putting in those stars, which special elements you put in those stars. And you can see that stars, right, so for instance, the star is always in the bottom. That means you, oh yeah, forget it, sorry. So, so you fix what you put in the stars, and then you count the remaining, filling of the remaining cells. So for instance, here we would say that this star must have 5. So the special element is 5, and this star must contain 5, and this star must contain 5, and the rest are arbitrary. That's, yes? But k is 2. K is the number of stars, and you always put your the maximum, the largest elements you will always put in the stars. The k largest elements. Okay. And that's very lucky. We are very lucky because the condition that we wanted, that the dict-path must be a sequence which begins with 0, is precisely this sort of a condition. Except, well, so more generally, if you want a dict-path with prescribed position of touch points, where points touch the diagonal, you put you draw this shape, just a single bar, and you put stars where you would have your touch points. And the corresponding unit interval order is non-positive integers. So remember when I said how the dict-paths correspond to a P-tableaux, I had to put the numbers backwards. I also can put them with a negative sign. It also works. And so that's what I will do. Then if you take the non-positive integers and the maximal elements are 0, and these are my special elements. And my condition is that I want these stars to contain zeros. Okay. So this, in this sense, dict-paths now are precisely tableau with satisfying my properties. Yeah. Okay. So there is something which is a bit confusing. Of course, you can allow some more special elements than stars, for instance. But then you can always say that, well, I just sort of consider those elements just zeros, but they're a little bit smaller than the other zeros. So there is always a way to kind of make everything work very, it's very true, but then it's not so intuitive. It's a bit longer to explain. So yeah, there are variations of this. That when you have some, so the stars must always contain those special elements, but you are sometimes allowed to put some special element somewhere else. It would correspond to counting dict-paths, where you say that a path must touch here and must touch here, but it can touch also somewhere else. So this is also allowed. These counting problems fit the picture. Okay. So it turns out that Shareshian-Wachs theorem can be generalized to this kind of counting. But instead of, so I don't know, some people who read our proof of the shuffle conjecture are acquainted with this space VK. So instead of symmetric functions, we have to consider this space VK. So it is space of infinitely symmetric functions in infinitely many variables, but not symmetric, but symmetric in all but k variables. One way to write it is say that we have symmetric functions in x, i's, and just polynomials in y's. Non-symmetricity, no symmetricity assumption. And then there is a pairing on VK. You have the, can say that Schur functions for in x's times monomials in y have a basis. Maybe that's not the best pairing, but for this statement, it doesn't matter. Any pairing will do. So this here is a theorem for each unit or interval order P, and you choose K, which is a number of those special elements in the end of the set. There exists an element chi pk in Vk. And for each generalized shape lambda with k stars, so where do you put this? There exists an element chi lambda in the Vk, so that the count, this Q count that we have, is given by the scalar product. So let's just say what is this chi. So you may ask, how explicit are these chi's? So remember, we always have something corresponding to a shape and something corresponding to a content. Now shape is generalized. You can have some stars and it's not skew shape anymore. And the content is also this P, this unit interval order. Okay. So let's separate these things. So first, what is this chi of a unit interval order? So again, in this proof of shuffle conjecture, we had something which is called character of a partial dict-path. So we had a recipe to compute the symmetric function associated to arbitrary dict-paths, but we kind of do it step by step. And this, in the intermediate step, you have to stop at some point of the path. And that point is not on the diagonal, it's hanging somehow. And that's correspond, the height at which it's hanging, it corresponds to this K. And this, okay. So we have, for instance, a way to compute this character on a computer. And it can be defined. So there was a definition in that paper, and then here in this context is defined by counting fillings of certain easy shapes. Easy means a collection of vertical bars. You remember that in a vertical bar, entries must increase very fast, and that correspond to so in this some other way they're counting chains in a poset. So you're counting chains in this poset. Maybe if you've heard about counting chains, you will be familiar. So it's made simpler to count chains, right? And how do we prove this theorem? Basically, it's the same as Shareshian-Wachs proof. We have to put, so if we have some chains, we put them together. Then there can be errors in the horizontal direction. Then we have to fix the errors. We choose the first error, we fix it by doing like kind of a move, and then you see that somehow you get some symmetric function in the end, which you. So here we don't have a very good formula for this chi corresponding to the shape. Yes? So yeah, it is, as I said, these functions, the functions that of Shareshian-Wachs are precisely chromatic symmetric functions. They count these chains in the poset, or in terms of incomparability graph, you can also say what they count. I just don't want to stop, but it's exactly what you have in mind, except. The question was, can you understand it in terms of the incomparability graph? And you say, yeah, of course, this is it's equivalent. Except one difference is that we have the stars and we put the special elements in the star. So, and then, so we have this statement. I'm moving towards applications, and then I will be open problems in the end. But so doing this, we discovered some new stuff. And this is, you can understand it as follows. So we have this symmetric function. We have these functions which are not symmetric functions. The elements of VK. And this VK is somehow generalization of symmetric functions. For me means symmetric functions. You generalize, you get this space of symmetric functions, symmetric in all but K variables. But then you kind of project to the new variables, and then you can symmetrize. Oh, something is missing here. It means you get again a symmetric function. So out of this element of VK, we can obtain Shareshian-Wachs symmetric function, but we can obtain another symmetric function by doing the other thing. You're forgetting the x's and keeping the y's. And this you can trace it in the combinatorics as follows. So we started with skew shapes. Now then we generalize. We say let's do the stars, put stars on shapes and allow columns to grow. But now we restrict it to sort of special shape, where a generalized shape is special if every row begins with a star. Some condition, but remember it's the same condition as we had for counting dig paths. We always have a star in the beginning. And you can do the same with contents. So first we generalize contents to unit interval orders, and then to obtain the corresponding set, which will be somehow dual to this one, we have to consider so-called connected unit interval orders. You can say a unit interval order is connected if the incomparability graph is connected. It's a very natural condition, but it's completely orthogonal to the situation when your unit interval order is just a normal ordinary order of integers. That's never connected. So somehow you had some situation, you generalize it, and then you restrict it to some other situation where you don't have any overlap. So right, the attack graph. Attack graph is just that incomparability graph. Because if you remember what it means for A to attack B, it just means that A is less than B and it's not comparable with B. Okay. So to summarize, we have two symmetric functions constructions. One is this Shareshian-Wachs chi-p, this chromatic symmetric function associated to a unit interval order, and we have this new function. It depends on the connected unit interval order and number k, which is the number of maximal elements you choose. Any number which is less or equal to the total number of maximal elements. Okay. So let me just, so what do we do with this? Oh, yeah. So it turns out in some special cases, we can compute the symmetric function associated to the shape. As I said, first, we had in the proof that it's not very clear what is a symmetric function associated to the shape. And it turns out that for shapes like this, for shapes like this, when you have a single bar with a bunch of stars, the corresponding symmetric function is certain modified Hall-Littlewood polynomial. So there are these creation operators for Hall-Littlewood polynomials. And so you have to take positions of the stars, give you a composition, and then you apply the corresponding creation operators to one, you get a Hall-Littlewood symmetric function. So that's one thing we can compute. But then there is more difficult computation, and it's very strange. So the result is very strange. So we consider a shape like this, where you put stars. So remember, so on the left, we have stars in the left part. And whenever we have a star, the column increases. But up until a certain point. And then after that point, we just have no stars and an ordinary Young diagram. Okay. So it turns out that that corresponding symmetric function corresponding to this shape can also be computed, and you get the Schur function, plus or minus Schur function, where you are supposed to take all this part with the stars. Oops. You take this part with stars and you straighten it out. You make it down. You make all of this then point down. So you get something like this on the right. So you kind of, if you want to go backwards, you have your Young diagram, you cut it along a diagonal, and then you draw the bars to the left instead of downwards. So the sign is a number of cells which participate in the process of straightening. It's a number of, on the right, it is a number of cells below the diagonal, the parity of that number. Notice that the row lengths on the left become hook lengths of the main diagonal on the right. And then our theory implies the following thing. If some, so I on purpose, I formulated not very precisely, but it is for the purpose of the talk. But its philosophy is as follows. If some enumeration of tick paths, parking functions, whatever you have, something can be reformulated in terms of unit interval orders. If that counting is given by scalar products f c alpha for some symmetric function f, c alpha is the Hall-Littlewood function. Then the corresponding enumeration of nested things, nested dick paths, nested parking functions, P-tableaux, is given by the scalar product with Schur functions. Yeah. So again, you can, maybe for you it will be easy to count one case, for instance, f with c alphas. Then the theorem will tell you, well, then the Schur functions are given in this way, in another counting. So that's the conclusion we obtained by studying this P-tableaux. Now I will formulate application and then pass to open problems. So we have this shuffle conjecture. There's this nabla operator in the modified McDonald basis is given by, it's a diagonal operator, multiplies every McDonald polynomial by certain monomial. And you can apply now nabla to some usual symmetric functions like Schur functions or any your favorite functions. And then you get sum of rational functions as coefficients, but like in Eugen's talk, you remember he had the sum with denominators, with sum over tableau, some kind. And by theorem proved by Garcia and Heyman, I think. So we have the denominators cancel out, and then observation will tell you that sometimes it's positive, and that's usually a conjecture. And one case of this is a compositional shuffle conjecture by Hagel, Heyman, Loehr, Remel, and Ulyanov that we proved together with Erik Carlsson. This conjecture says that if you apply this operator to the elementary symmetric function, you get some enumeration of parking functions. And parking function is, as I said, is a dig path together with a labeling of vertical steps by integers satisfying certain properties. And in fact, so this is a compositional shuffle conjecture, which means that there is certain refinement. It turns out that elementary symmetric function is a sum over all compositions of this Hall-Littlewood's, and the nabla applied to each Hall-Littlewood is positive and given by paths having prescribed touch points. So if you remember what I was saying before, it's precisely fits the framework. Now there is another conjecture, Loehr-Warrington conjecture, which is now published. No, not published. I mean, no. So it's in the preprint by these 5 people, which I'm sorry, I embed these names. So Blasiak, Heyman, Morse, Pan, and Sillinger. Yeah. Okay. So that gives you nabla of a Schur as an enumeration of nested parking functions, plus or minus. I forgot plus or minus here. And so we had this. Okay. Now, so what do we do with this? We just move nablas to the right. In terms of saying what nabla f scalar product with some complete homogeneous function, we say it's the same as f scalar product with nabla conjugate operator to nabla applied to the complete homogeneous function. And then basically both conjectures from our theory are equivalent. They are just equivalent to the statement that this conjugate of nabla applied to the H is a weighted sum of chi p, those new kind of symmetric functions associated to unit interval orders, or some collection of unit interval orders, where you can make it explicit what unit interval orders are. And it turns out they're very natural. You have to take this z less or equal 0, but a is much greater than b if a is greater or equal b plus n. N is fixed here. And you consider those unit interval orders, the suborders of this, all suborders of this, but you weigh each by a power of t. Remember, we never had t in the story, but now everything must depend also on t. So there is a power of t weight. And yeah, so from our point of view, so we kind of made these conjectures, the theorems equivalent. So we had the proof written down, but we kind of, it just was lying on the desk. So now these people already have their proof. So we don't say that it's our theorem, but okay. Yeah. So the same works for powers of nabla, and we didn't check the details, but seem to work in the rational case. So now all these conjectures are just part of the same picture. And then there are many open problems. Can I have 5 minutes because I started later? Yeah. Okay. So now remember we have two ways of associating a symmetric function to a unit interval order. One of Shareshian-Wachs and another one that we have with K. So let's about this one, Shareshian-Wachs function, which is the chromatic symmetric function. So there is this famous Stanley-Stembridge conjecture. Its refinement says that this chi p is H positive. Refinement means it's because it has Q in it now. Now every coefficient in Q is H positive. So there's some ideas. So I think really this P-tableaux should be studied more. So some sort of Jew that I can on P-tableaux would prove this conjecture. And this is sort of somehow well known. People tried to construct it, but failed. So maybe it's not possible. Maybe some other should be some other kind of Jew. Then this interesting question, you have shapes giving you some symmetric functions and contents giving you symmetric functions. Why don't you interchange them? So in the classical situation, this is given by Zelevinsky's pictures. It's kind of things which you have two skew shapes and they tell you what sort of things to count to get the correct scalar products. And so again, if you had something like this for P-tableaux, it would be proven. We're asking for some algebraic structures on P-tableaux. For instance, affine Hecke algebra representations. There are these representations by Arun Ram, I think, with basis given by skew tableau. What maybe some kind of algebraic structure is associated to P-tableaux. Okay, that's all we have for this. Now about our symmetric function. So one thing is that we have some positivity. So we have a collection of functions. You want to find some natural basis in which all of them are positive. So it turns out that the corresponding basis conjecturally is given corresponds to a canonical basis in the affine Hecke algebra. So I don't know if that's well known. In the usual finite Hecke algebra, it's kind of classical. We have these Kazhdan-Luistik polynomials. Here we have affine Kazhdan-Luistik polynomials. They can be defined in the same way as in the finite case by some procedure where you have some pairing and you have some basis, and then you make it canonical. You can do this procedure for a fine Hecke algebra, get some basis, and it seems in experiments that you get our functions are all positive, and positive in a very nice way, somehow, optimal way. So correspondence is given by that if you have an element in a fine Hecke algebra, you can apply some symmetrize it on one side, you get a polynomial, a Laurent polynomial. And that corresponds to polynomials in Y variables. So we are asking for more generally canonical basis in the larger space Vk, which contains both symmetric functions in X and polynomials in Y. And why there is a strange sign Schur positivity. So our functions are expanded in the Schur basis. They're not positive, but some Schur functions always appear with plus, and some Schur functions always appear with a minus. So all our functions conjecture. So okay, we have a proof that this is the case for our functions because of the explicit formula. But for instance, now as we have this canonical basis, it seems to be true also for that basis, and we don't, and that's we don't know why. Yeah, strange. So I'm asking if somebody has seen this sign Schur positivity in nature. And then I just last slide. So geometry. So for chi p, Juliana explained that there is a geometric interpretation of that symmetric function using Hessenberg varieties. Cohomology of Hessenberg variety, you take the symmetric group action and you decompose into irreducibles. You get chi p. And we have we can prove that our symmetric functions can be obtained in the following way. You take usual Hessenberg, and there is certain open subset there. So let me spell it out. So we fix unit interval order, which is the same thing as the Heisenberg function. We have some number k, and you choose a regular semi-simple element gamma. And we take flags satisfying these two properties, that gamma applied to fi is in the, this is a Heisenberg function here, in the little bit larger space. And then you start with fi, hi. And our condition is that fn minus k does not contain any coordinate line. It's an open subset. Here is example. You take your Heisenberg function is just n. So the first condition is vanishing. And you can take also partial flags, in fact. And so here is one example. You take Pn minus 1 without coordinate hyperplanes. Our second condition will say remove coordinate hyperplanes. What do you get if you get the torus, right? C star to the n minus 1. The action of the permutation group is just permuting the coordinates. So the cohomology of the torus is exterior algebra. It's a sequence of all exterior powers over n minus 1 dimensional vector space on which permutation group acts. So which representations of the symmetric group do you get? You get hooks. As we see, hi of this space is precisely the ice hook. Okay. Ice hook has exactly I cells below the diagonal. And it is in hi. So it seems this should be not coincidence. There should be some large class of spaces with these properties. And the examples are given by our what we call open Heisenberg varieties. So they have this as cohomology is given by these functions which are sometimes Schur positive, sometimes Schur negative. And we conjecture that their positivity, negativity can be explained by this cohomology fact. Here is the main conjecture. So some spaces, in particular open Heisenbergs, conjecture says that they have the property that for a partition lambda, the corresponding SN representation appears only in one cohomological degree, in H iota of lambda, where iota of lambda is a number of cells under the main diagonal. So the hooks, for instance, it works for the torus. And we don't have many more examples. Okay, that's it, I guess. Thank you.
We have 1 or 2 minutes for questions. Are there any questions in the room? Bruce.
Right. Yeah. Yes. I said that. Yeah. It's what? Yeah, but if you really, you're right. That the comment was that Semmelweis-Steinbridge conjecture is about some function being E positive, some function which is already Schur positive being moreover E positive. But it's so if you're really careful, there is some involution in the process which interchanges E and H. So that's what we get. Of course, you can formulate in E. It's the same thing. Say again, please. The question is if this can be generalized to a path below a curve, some curve, like in some other talks. No, no. Okay, I can of course there is some interesting thing you can do. you can consider periodic unit interval order, like think about it on a circle. But whenever you make a round, you get a power of t. If you pick an element which is somehow higher, then you should have weighted with t. And it seems that for the rational shuffle conjecture, it just works. So the straightforward generalization of our approach to rational shuffle conjecture would tell you that you should consider instead of this line, that you should consider this infinite unit interval order, maybe following the line, and then try to see maybe you get something. How do I? There are many questions in the chat. Okay, you were moderating, I see. But it's higher. Oh. It is nice that the strange sign does correspond to my original Schur positivity conjecture about nabla of strange sign Schur later given the combinatorial setting by Loehr. That's exactly what I was talking about. That the strange, that's where we got it out from, right? And that's the same Schur sign. And the question, there is a question. Do you get the effect of delta operators by relaxing conditions about a special shape and connected UI or conditions? Do you have some ideas of any mechanism? Well, no, we didn't touch delta conjecture at all here. I hope everything that worked. I hope this approach will help you also to understand delta conjecture.
I'm going to call a halt to the questions there in order to leave time for graduate students to speak with Anton. Thank you again for a marvelous